All right, so in this video, we're going to be talking about coordinate systems in linear algebra. And we're going to start with some basics, and then we're going to work up to doing transformations, transforming from one coordinate system to another. All right, so when we begin to work with vectors, we often end up getting so accustomed to the standard way of presenting vectors that kind of forget what the sort of notation is actually trying to communicate to us. So when we start working with different coordinate systems, different sets of non-standard basis vectors, they can be a little bit confusing. So we're going to kind of break down what we are actually working with in the standard basis, and then how that relates and how that translates into working with non-standard bases. We're going to look at it graphically in 2 dimensions as a basis for our sort of intuition and our intuitive knowledge of it. And then we'll do calculations on larger systems, R3, R4, etc. All right, so let's start with some basic terminology and notations. So a basis is a set of vectors from which a coordinate system is built. Every basis has enough vectors to span the entire vector space, but not so many that the set becomes linearly dependent. That ensures that we can reach every vector in the space, but so that our solutions, our representations are unique. So the number of vectors in a basis is the standard way of talking about the dimension of a space. So a space like R2 will always have 2 vectors in any set of basis vectors. R3 will always have 3 vectors in any basis, and so forth. Now, the set of standard basis vectors is notated typically by a capital E, often sort of in nasty cursive form, but typically E for some reason. Probably elementary is probably what it stands for. And then the elements of the standard basis vectors themselves are also numbered with a lowercase e, E sub I. So in R2, E1 is 1, 0, and E2 is 0, 1. And so they're always represented as basically a 0 vector, except with a 1 in the position of the subscript. So in R5, we would have 5 basis vectors, and they're given by E1 is 1 with 4 zeros, E2, 0, 1, and the rest zeros, E3, 0, 0, 1, and the rest zeros. E4 would have a 1 in the 4th position, and then zeros everywhere else, and E5 would have a 1 in the final position with zeros everywhere else. So this is, again, just some standard notation. Now, geometrically, what are we thinking about? The E1 vector is basically 1 unit over in the x direction, and E2 is 1 unit up in the y direction. And so when I think about a vector v, what this is essentially saying is these are the coordinates that I'm multiplying, the constants that I'm multiplying by each of my corresponding basis vectors. So 2 in this position means it's 2 times E1, my first standard basis vector, and the bottom component means that I'm taking multiple -1 times the y basis vector, which would be E2 in linear algebra. And sometimes in Calc 3, we represent these as I and j in the 2-dimensional system, and I, j, k in the 3-dimensional system, but that is E1 and I and E2 and j are literally the same vector. Again, it's just about standard notation in multivariable calculus. We're almost certainly dealing with 2 or 3 dimensions. It's only in linear algebra where we're like, okay, I'm going to run out of letters if I keep doing this. And so we introduce a different notation with subscripts in order to account for it. So what we're essentially saying, if we were to plot this on the graph, is that we're going to multiply E1 by 2. So 1 copy of E1, 1 copy of E1 gives me 2 copies of E1, and then -1 copies of E2 gets me here. And so if I add these 2 vectors together, my 2, -1 vector is going to meet at the corner of that, again, that parallelogram. It's a rectangle in the standard basis vectors because the standard basis vectors are all orthogonal to each other. And so you end up with a vector that points in this direction. Now, it's true that for any vector in any basis system, if I express that vector in that basis, I'm going to express it as the coefficients of the basis vectors in order. And so this would represent C1 times the first basis vector and C2 times the second basis vector. Now, if I change my basis vectors, then this these coefficients will then be a different point in space. Or if I want to represent the same point in space, I would need different multiples of the basis vectors in order to get to that point. So that's part of the difficulty we have here, is to understand what we're doing when we transform into a non-standard basis. Now, if we consider our basis vectors, again, in our basis typically expressed by capital B, often in script form, it's given by these two basis vectors, 1, 1 and -1, 1. So basically, we're creating a grid on the graph instead of based on E1 and E2, we're creating a grid based on B1 and B2. And so B1 in the standard basis would be 1 over 1 up. That would give me this vector. And in the standard basis, that would give me 1 over and 1 up in the other direction. That would give me B2. And so now, when I'm trying to represent my 2, -1 component in this new basis, I need to figure out what do I need to multiply B1 by and B2 by in order to end up at the same location that I was in my original coordinate system. So this system is actually rotating my original coordinate system by basically 45 degrees. And I'm also, actually, the vectors are a little bit longer than they were before. Now, I'm actually missing a minus sign in this expression right here. But if I want to solve for C1 and C2, I'm essentially setting up a system of equations. What do I have to multiply 1, 1 by? And what do I have to multiply -1 by in order to arrive at this same destination, 2, and again, this should be -1. So if I solve this system, then I will get the vector representation in this basis. But that's just a vector form of a linear equation. And so I can actually put this into a matrix, 1, 1 in the first column, -1, 1 in the second column, and 2, -1 in the first column, in the third column, and then row reduce that to get my coefficients. And when I do that, I end up with, if I go 1/2 over in the B1 direction and -3/2 in the B2 direction, then I end up, when I add those together, to get to my final destination point that I was shooting for. So that would be the representation of the 2, -1 vector in that component. Now, I could, in some contexts, choose, rather than dealing with the the basis vectors that are a little longer, I may want to normalize them to make them unit 1 vectors. I could do that by rescaling them in this direction. By both of these have a length of square root of 2, so I could rescale them. They also happen to be orthogonal in this particular example, and so later on we're actually going to talk about how you can sort of shortcut the process a little bit if you have orthogonal basis vectors. but we wanted to look at an example that did not require them to be orthogonal. Now let's look at another example. So here I have a basis D, which I have basis vectors 3, -2, and 1, 2 as my basis vectors. And again, these are expressed in the standard basis. So my first basis vector is actually this green line, this black line right here. And my D2 is in this direction. And again, I've changed the grid lines on the graph here to indicate that this is one copy of D1, and over here is 2 copies of D1, and then over here is -1 copies of D1, and so forth. So we can kind of visualize what we're trying to accomplish. And then similarly, 1 copy of D2, 2 copies of D2, -1 copies of D2. They're forming this grid 1 unit by 1 unit at a time. But the units are not the standard basis vectors, they're the copies of these vectors. So similarly, I can set up a system of vector equations, some constant times 3, -2, and some other constant times 1, 2 is equal to 2, -1. I can convert this to an augmented matrix in order to solve for C1 and C2. And what I get is 5/8 of D1 and 1/8 of D2 will get me to the point in space that I think of as, on the standard basis, 2, -1. And we can always verify that our calculations are correct by simply multiplying our corresponding basis vectors by the coefficients that we find. So for instance, if I multiply 5/8 by 3, -2, I get 15/8 and -10/8. And if I multiply 1/8 by 1, 2, I get 1/8 and 2/8. And if I add those together, I get 16/8, which is 2, and -10 plus 2 is -8, which is -8/8, which is -1. So the arithmetic does work out here. So this is the geometric interpretation of coordinates in other bases besides the standard basis. So we want to solve for coordinate values in a different basis. We can use a number of different techniques. We're going to discuss a couple of different situations as we continue. So converting between the standard basis and the non-standard basis, or vice versa, we're going to look at converting from one non-standard basis to another non-standard basis or back. And then also the special case of converting between the standard basis and an orthogonal basis. So we mentioned earlier our first example, the vectors were actually orthogonal, and there is actually another strategy that we can use besides that vector equation in order to find those coefficients. That it's a bit more efficient than the standard one. Now, in our first example, we're going to again look for a more efficient way of calculating the coordinates for converting between the standard basis vector and one non-standard basis. Now, essentially, if we set up our matrix equation as we had before, where B1 and B2 are the basis vectors and C1 and C2 are the coordinates, then what we essentially can write is a matrix that has B1 and B2 as the columns of a matrix, in this case in R2. And then the component, the coordinates, the things that we're trying to find are like our old x1, x2, the unknowns that we want to solve for. That's our component, our coordinate vector. And then we set that equal to the vector in the standard matrix representation. So in the E1, E2 coordinate system. Now, if we call this matrix that has the columns of the basis vectors, we'll call this P sub B, where B is the basis that we're working in, and C1 and C2 represents the basis, the coordinates in that basis. Then what we get is this equation that PB, this is the coordinate transformation matrix, our vector in that coordinate system is equal to the vector in the standard basis. And if I want to go in the other direction, so I don't want to transform my basis in the non-standard basis into the standard basis, if I want to find the basis representation, the vector representation in the new basis, then I need to multiply both sides by the inverse. And so I'm going to multiply my vector in the standard basis by the inverse of my coordinate transformation matrix. And then the output of that will be the coordinates of my vector in the new basis. Now, this is totally consistent with everything we've done before. We set up a system of equations, multiplying by the inverse by our constant solutions is actually another way of solving our system of equations. So all we've done is we've changed the notation, and we've talked about using inverses instead of solving a system of equations, but this is an equivalent procedure to what we were doing before. So let's look at a specific example. Let's consider our basis f is composed of these three vectors, 1, 3, 4, 5, 0, -1, and 2, -2, 1. And the vector that we want to transform from the standard basis into the new basis is -5, -2, and 15. This subscript should say F now. So first, we're going to construct our P matrix, our coordinate transformation matrix, and that is just putting these vectors into the columns of our P matrix. And then we want to find the inverse of that. Now, I did this using technology in my calculator. I entered this into my calculator and I found my inverse, and I got this expression for my inverse. And now if I multiply my inverse by my vector in the original coordinate system, then I end up with the result of 2, -3, 4. Now again, what does this represent? This means that I need 2 times my first basis vector, -3 times my second basis vector, and 4 times my third basis vector. And if I do that arithmetic, I do in fact end up with my -5, -2, 15, which was the original vector in the standard basis. So in this system of bases, the components that I need are 2, -3, 4. Now, we're going to convert from one non-standard basis into another one. Then I want to find a relationship between them, and the relationship between them is the representation in the standard basis. So let us consider, I have a basis of vectors B, and I have a basis of vectors I'll call C. In both cases separately, I know that if I create a matrix of the coordinates basis and I have a representation for that basis, for that vector in the standard form in that vector, that basis, I know that these two sides are equal from the previous illustration. And I also know that if I can do the same thing for the C vector, so if I have a C basis, I can create my matrix of those basis vectors. This vector will represent the coordinates in that system. And I know that if I multiply them, then I will get the standard basis, the form of the vector in the standard basis. Well, I have x equals the form in the standard basis in both of these equations. And so I can set the equations equal to each other. Now, if I want to solve for one of the basis forms, then I simply use an inverse operation in order to get that thing that I'm solving for on one side of the equation by itself. So if I'm trying to solve, for instance, for the representation of a vector in the B basis, and I want to solve for it in the representation in the C basis, then my equation will become multiplying by the inverse of the C basis, and then multiplying by the basis in the B coordinate system times the representation in the B coordinate system. On the other hand, if I want to solve for the basis B, then I would do the inverse on the other side, and I would get PB inverse PC times x in the basis C. Now, sometimes you'll see this notation, and some textbooks will use the this representation in what I sometimes think is a confusing order, but they're trying to match the subscripts in basically our inverse times non-inverse sequence. So you may see this notation P with a C and an arrow B. Now notice the direction of the arrow is going from B to C. So what they're saying is that this product of two matrices here can be thought of as the matrix that transforms a vector in the basis B into a vector in the basis C. But it's just represented by this. And sometimes, again, you will see this replaced in this notation. But again, they're trying to remind us of the order we're doing the multiplication in, the vector that the destination basis that you're ending up in is the inverse, and the one that you're starting out in is the non-inverse. Likewise, if we're trying to get to a basis B, then the notation would be going from C to B in the subscript. And that's because on the left, you're multiplying by the PB inverse, and on the right, you're multiplying by the standard B, PC. Now, it is also the case that if you are familiar with how inverse property is applied, that if you take the inverse of the B transforms to C matrix, you will get the C transforms to B inverse operation. So they are, in fact, inverses of each other. They are related to each other. They are literally doing the opposite things. One is converting from B to C, and the other is converting from C to B. So let's walk through a calculation. So I have a basis F that we saw in a previous example, 1, 3, 4, 5, 0, negative 1, 2, negative 2, 1 is our basis. And we have a second basis, G, 1, 0, 2, 2, 2, 3, 1, 0, 0, 1, 0, 1. And we're given the representation of a vector in the basis F as 2, negative 3, 4. So again, that was the one that we saw earlier. And we want to convert this directly into a G representation without going through the standard form. So we're going to need to construct our PF and PG matrices. So again, this is just the non-inverted version is just the vectors of the basis in the matrix as is. Now, in order to construct the F goes to G matrix, I'm going to need to find the inverse of the G matrix. So I use, again, my technology in order to do that inverse. And I got this result for my inverse. And then going from F to G, that matrix is PG inverse times PF. And so I multiplied PG inverse times PF. The order of multiplication does obviously matter in linear algebra. And the result that I got was this. And so I'm going to multiply this by the F vector, the representation of my vector in the F basis. And when I do the multiplication of this matrix times this vector, I end up with 21, negative 1, negative 24, which is the coordinates of this vector in the G basis. Now, again, if you're doing transformations between multiple coordinate systems, do not be surprised in the general case that you don't necessarily get nice whole numbers. Sometimes it can be very difficult to insist on getting whole numbers and all of the different representations. They are very carefully chosen problems if you do get nice vectors in every single system that you try. So again, just don't be too surprised if you get fractions in one or more of these forms. Do they represent the same vector in each basis? Well, we can check by taking the coordinate system in F here, multiplying by the basis vectors in F, and we get -5, -2, 15, as we saw in a previous example. But if I take the coordinates from the G basis and I multiply them by the vectors in the G basis, I do also get -5, -2, 15. So they are representing the same vector in the standard basis, but representing them as coordinates in their own vector system. Now, one question that might concern us is that what do the vectors in the matrix that converts from F to G, what do they represent? Well, if we think about F1 as my 1, 3, 4 vector, that's my first component vector. If I multiply PG inverse by that vector, what I'm essentially doing with this matrix that transforms the vectors from F to G is I am converting each of the basis vectors into a representation in the G basis. So let's think about this column here, 3 halves, 3 halves, -7 halves. That is, in fact, the first column of my F convert to G matrix. So this matrix represents the vectors in the F basis, but represented in terms of the G coordinate system. And then when I multiply by the coefficients, I'm getting the final representation in the G basis. So that's what those vectors represent. Now, in our final example, we're going to look at orthogonal bases. So if we have the special case where our vectors in our bases are perpendicular to each other in traditional coordinate systems, or orthogonal more generally, because we can also apply definitions like this to like function spaces and things like that, if we're dealing with those kinds of vectors. This more general definition can be very powerful, and we actually encounter applications like this in a wide variety of coordinate systems that you might not think of as being orthogonal vector spaces, and finding coordinates of how do we represent those in that space. But in the specific case of our vector spaces, let's walk through an example. So we have the basis B. We're going to assume that the basis vectors are orthogonal. Then the representation of the vector in the standard basis in that B basis is going to have the coordinate x dotted with our vector basis component divided by the magnitude, essentially squared, of the basis dotted with itself, the vector dotted with itself. So this is the dot product is sometimes used as a magnitude. The square root of the dot product is equivalent to the length, and so this would be the length squared, but it's the vector dotted with the basis vector divided by the vector dotted with itself. So let's look through this example, and we'll do it both by an example using the dotting method, and then we'll use the method that we talked about with the matrix transformations in the previous section and see that we get exactly the same answer. So let's consider the basis, 3, 2 and -3, 2. You can see that if you dot these two vectors together, you do in fact get 0, and so they are orthogonal to each other. Now, they're not length 1, but they're orthogonal to each other. Now, if we want to find the representation of the vector 5, -7 that's in the standard basis, we want to find how it is represented in this basis, then we're going to apply our formula. So we're going to dot x with B1 divided by B1 dotted with B1. And that's going to be 5 times 2 is 10, and negative 7 times 3 is negative 21. It's going to give me negative 11, and B1 dotted with B1 is 4, and 9 is 13. And I get this. So in C2, the second coordinate, I'm going to do the same formula, but I'm going to now dot it with B2. So 5 times negative 3 is negative 15. Negative 7 times 2 is negative 14. I'm going to end up with negative 29. And my denominator, 3 squared and 4 squared, is going to give me also 13. So what this is saying is that the coordinates in this basis, for this vector, are negative 11 over 13 and negative 29 over 13. Okay, well, if I check this, I make my PV matrix of my 2, 3 and negative 3, 2. If I find the inverse of that matrix, I get this matrix. I multiply by the vector in the standard basis, 5, negative 7, and I end up with exactly the same coordinates as here. Now, this calculation was a lot easier than finding the inverse of this matrix if you had to do it by hand. And certainly, the bigger that your matrix gets, the more efficient, computationally efficient, this procedure will be. But again, this procedure only works if the vectors in the basis are orthogonal to each other. If they are not orthogonal, then this process will not work.